to first thank the organizers to invite me to this very interesting and important event. It's very hard, I would say impossible, to overestimate the influence of Rodney Baxter's work in this field, in theoretical physics in general, but the whole field of integrability in particular. I was very much inspired by his work as well, even though I never met him in person. I mean, I also went into integrability rather late, I would say maybe 10, 15 years ago. I started to look more closer to integrable systems, but still I got incredibly inspired, and it was incredibly fun to work with. So I will talk about some possible application of integrability to physics or to non-equilibrium statistical physics, in particular to a phenomenon which we have come across recently, which is connecting Kardar-Parisi-Zhang scaling to integrable magnets, to integrable systems. And I will tell you a story. I will tell you basically a short story, starting from physics and from playing with numerics, simulating dynamics of many-body systems. And then I will close with describing what I believe a beautiful model, or a family of beautiful integrable models, which I believe are minimal models which maybe contain explanation to this physics, even though we have not yet found explanation. So I will try to pose a clear conjecture. Okay, so this is basically guys from our group in Ljubljana who have been at some point or another involved in the projects that I'm going to discuss. A senior collaborator, professor in Ljubljana, Marko Žnidarić, and then the bunch of, at that time, PhD students, Bojan, Marko, and Žiga, and Enei, who is also senior researcher in our group. Okay, so I will just go start with this kind of flashy slide, which try to kind of explain why these models are so exciting, and what are these models? I mean, everybody knows six-vertex model, or XXZ quantum Hamiltonian, the two being closely related. And you can even make them even more closely related by not caring about Trotter formula, but just take finite time trotterization of XXZ quantum Hamiltonian. Then you really get a six-vertex model for the quantum propagator, but not in the stochastic, but in the unitary regime. So the gate is just the R matrix of six-vertex model written as a unitary matrix. If you and that's just an example of dynamics which is completely integrable, which is unitary, which is, it has all the features of generic interacting integrable dynamics. And this six-vertex model is actually a rich family of models which can go from isotropic, from, let's say, easy axis, isotropic, and easy plane quantum magnet, right? And this is indicated in this diagram where I just parameterize the gate. Of course, this is not a canonical parameterization that people in integrability would use, but it's very physical parameterization where you single out two coupling constants. One is the coupling of two spins in XY plane, and the other is coupling of a spin in ZZ, so Ising coupling in the Z direction. Depending on the two couplings, this is the phase diagram, you find these different regimes, which are the blue, red, or yellow. Blue meaning, and this on the right-hand side of this panel, what we plot is the dynamical exponent. That is the growth with which, for example, the transferred magnetization between left and right half of the system, when you slightly magnetize it, grows as a function of time. It's important that you only slightly magnetize it, so it's important that you are close to equilibrium. Then you have universal growth of magnetization depending on the dynamical regime. In particular, if you are in the red phase, red phase is easy plane is like critical Heisenberg, critical XXZ if you want, where delta, the usual parameter delta would be less than 1. This would correspond to dynamic exponent equal to 1, which means ballistic transport. In the other regime, which I denote in blue color, this dynamic exponent, which is basically the inverse of dynamical exponent as it's usually referred to in non-equilibrium statistical physics, but it's the exponent with which the growth, with the growth exponent, alpha, it's a standard growth exponent, well, more or less. It's this one is now going to 1/2. So it's the two kind of regimes. One is diffusive, the other is ballistic. But what is really interesting is the intermediate regime, which happens when you have an isotropic case, when J is equal to J prime, where the growth exponent is 2/3. And well, I mean, just to tease you a little bit with the old story, I mean, if you go to the ballistic regime, the situation is even more interesting. You can compute the so-called ballistic transport coefficients, or in solid-state theory, people call this Drude weight or spin stiffness. If it's high temperature or infinite temperature Drude weight, if you plot it as a function of anisotropy parameter, in this case, I write it as cosine eta. Eta is related, as you know, also to deformation parameter. I mean, Q is e to the I eta. So it roots of unity, right? At roots of unity, we know that quantum group has very special representations. So at roots of unity, we find that this has very strong physical consequences, namely the ballistic transport coefficient has delta spikes. And these delta spikes are organized in a fractal fashion. So there is delta at any rational root of unit, any rational point, any rational anisotropy corresponding to higher and higher orders of roots of unity. And that means that, we have this kind of nice fractal. Yeah. And these fractals actually are not kind of just academic mathematical physics, but they are actually physical. I mean, they are easy to see now in real kind of numerical simulations. Yes, let's say not yet real experiment, but so far numerical simulations. But we are probably not far from seeing those in kind of, let's say, quantum simulation labs. Anyway, but in quantum simulation labs like Google Quantum AI, they have actually already implemented this model. And this is already a paper which is a couple of years old in the group of, as I mentioned, Quantum AI, a group in Santa Barbara, which was based on a previous work by Igor Alainer, who kind of proposed a kind of quasi-particle picture of this XXZ model in discrete time. So the idea is basically to go directly to digital quantum simulation, so not to care about Trotter limit, just to run dynamics in discrete time steps. And so you can actually, it's a flow case system, it's a driven system. There is no conservation of energy, but still there is integrability, which means that there is a quasi-particle picture, and they are well-defined. Quasi-particles have well-defined dispersion relation. There is again bound states of magnons, so there are strings, and so on. So and in 22 in this Google quantum lab, they have actually simulated dispersion relation for the quasi-particles and actually real-time evolution of some interesting initial conditions in this model. But going back to numerics, of course, what theoretical physicists have to do every day is to run numerics, to run simulations of toy models. And we have run numerics on XXZ model for many years. For example, in 2017, we came across this kind of observation that if you look at this, again, two-point function at high temperature, or better, at infinite temperature, or simple, what some people would call a non-equilibrium quench, a weak non-equilibrium quench, where you start from a density matrix, which is close to infinite temperature Gibbs state, but you just excite it a little bit on the left, you just magnetize it a little bit up, and a little bit down on the right, which means that the mu, which is the magnetization parameter, is a small parameter. Yeah? If this mu is a small parameter, in these simulations it was of the order of 1/100, then you can deduce, this is just linear response theory, you can deduce two-point function. This would be a one-point function out of equilibrium, but using kind of Kubo-like ideas, you could reduce it, you could map it to a two-point function in equilibrium, which is what is plotted here. And this is the isotropic case, and this is the easy axis case. And this curve denotes the line, which is x is t to the 2/3, and this is x is equal to 3/2. So this is t is x over to the 2. I mean, it corresponds to growth, which a dynamic exponent 2/3, and here with 1/2. Yeah. So it suggests a dynamical exponent 2/3 directly from observing real-time evolution using DMRG or time-dependent DMRG numerical simulations. You can be a bit more accurate, right? You try to determine this dynamical exponent or running dynamical exponent in real time, and you find that you really have a clean convergence in the regime. This would be regime delta equal to 1, anisotropy equal to 1, so no anisotropy, isotropic case, and this would be anisotropy equal to, I don't know, 2, I think, or 3 or 2. And you see that in this case, you converge to 2/3, and in this case, you seem to converge to 1/2. And on the left, for delta less than 1, you would converge to 1, but I don't show it. So we have this kind of phase diagram, which I already showed before. Now, this has been actually observed even earlier in previous simulations, also in our group by my graduate student at that time, Boyan and myself, we have looked into a classical family, classical models, which are kind of classical versions of XXZ. I mean, I learned about these models in a book by Fadiev and Takhtajan, and we call these models lattice Landau-Lifshitz spin chains, even though later I was kind of informed that you should be better to call these models Sklianin models or even Ishimori chain. I mean, some people, most of people would call this model Ishimori chain, in particular when you refer to isotropic case. But this model again have a parameter, a deformation parameter, and you can go from easy axis to easy plane, and you see again a transition between dynamic exponent, 1/2, 2/3, and 1. Yeah, this would be like correlation functions, spin-spin correlation functions in different regimes, ballistic, intermediate, isotropic, and diffusive, and then you would have decay of current correlators. Now this is current correlators, which directly enters Kubo formula for the spin diffusion constant. You see that in the easy plane case, you have constant current correlator in long time. In easy axis case, you have fast decay of current correlator, meaning finite diffusion constant. But in the easy plane, I mean, in the isotropic case, you have something which decays with roughly 2/3. This was 2013, more than 10 years ago. And we had no idea why this should be 2/3. So we have just, reported observations. And then there was roughly even around the same time, even slightly before, Marko Žnidarić, our colleague, had actually published an observation following from steady state solutions of boundary-driven Limblad equation. So it's an open system, open in the sense of being dissipated at the boundary, not open in the sense of having just open boundary conditions, but having actual dissipative boundary conditions which provide current through the system. This can be implemented in terms of the so-called Limblad equation. And Marko observed that actually current as a function of system size, steady state current, does not grow as 1/n. In his paper, he denoted n as a system size, little n. So not a 1/n, but actually 1/square root of n. So it's not constant as in ballistic case. It's not 1/n as in the ohmic case, but it's 1/√n as some sort of super diffusive case, right? And it turns out that actually that's consistent if you go from space to time. If you go from steady state picture to quench time-dependent picture, then this is consistent with arguing that the dynamical growth exponent would be 3/2. And then there was this paper, I think, which kind of changed really, I mean, it kind of made a lot of, raised a lot of interest, where we kind of pushed these numerical simulations even further. And we tried to compute a two-point function. We try to deduce two-point function, not only dynamical exponent, but also the precise scaling of the two-point function, spin-spin two-point function. And we found cross sections of two-point function. I mean, this is precisely this kind of plots. If you make a cross section at equal times, and then you try to scale data, right? Dividing x's by t to the 1/2, right? Assuming that it is 2/3 exponent, you've got this very nice scaling with a slope, with a curve, with a scaling curve, which was not a Gaussian, which you might naively suspect by just looking at very crude numerics. But when you try to push your computers, for months, and try to deduce best possible data you can get, you see that there is a scaling function which is clearly non-Gaussian, but it has a quicker decaying tails. Namely, these tails decay not as e to the minus x squared, but maybe as e to the minus x cubed. And it turns out actually that they agree very well with the so-called Prachhofer-Spohn scaling, which Prachhofer and Herbert Spohn have obtained for polynuclear growth model, which is in KPZ universality class. So it's believed to be now a kind of universal scaling for two-point functions in KPZ universality class, which is, by the way, completely different physics. It's a physics which usually happens far from equilibrium, but what we are doing here, we are simulating systems at equilibrium. This is equilibrium transport, if you want. So why is that? I mean, this is actually a very kind of puzzling observation. And first of all, I mean, the question is why is that? I mean, what are the needed ingredients to observe this kind of KPZ scaling? And it seems that what is crucial is that ingredients are that your model is integrable, one, and two, that the model has non-abelian symmetry. Namely, this only happens at the isotropic point of XXZ. I mean, I will argue in the second part of my talk why this non-abelian symmetry is so crucial. But at the moment, just believe me, I mean, many models have been tried by different groups, And it's been consistently observed that this kind of KPZ scaling only happens at equilibrium. So at equilibrium first, in states which are non-abelian initial states, so Gibbsian states with non-abelian symmetries, dynamical evolution laws which have non-abelian symmetries, and they should be integrable. So, I mean, this is just the dictionary, which is a very, very kind of provocative dictionary, which does not have to do much with the truth, because we are comparing an equilibrium model with a far from equilibrium classical system. But if you identify your height function from KPZ with, so that the gradient of the height function with the magnetization, then you get a one-to-one mapping. So we get, yeah, we basically can use results from KPZ theory. Okay, there have been many kind of papers following these observations, starting from 2019. Of course, I only list the beginning of this reference list because now there are many more. But I think I would particularly like to emphasize these two papers, in particular the first one by Saran Gopalakrishnan and Roman Vasseur, who were able to explain this 3/2 exponent from a self-consistent theory based on beta ansatz, based on thermodynamic beta ansatz. So they kind of argued that, knowing the quasi-particle content in isotropic XXX, or in this later paper, they also extended this to arbitrary integrable systems with higher kind of rank Lie group symmetry, non-abelian Lie group symmetries. But in any case, I mean, the simple dispersion relation for the strings of quasi-particles, for the infinite strings of quasi-particles, uh, allows us to conclude by a self-consistent argument that the dynamical exponent should be 3/2. So that's not a proof. I think I call it a self-consistent argument, but it's a bulletproof argument, so I cannot argue against it. Okay, so this I think at least explains part of the observation that dynamical exponent should be 3/2, but it does not explain the link to KPZ scaling. So, and then there are people who then do experiments who picked up this story, and there was in 2022 there was a paper in Science by Emmanuel Bloch's group, who again observed in cold atom setups. They nicely observed dynamical scalings. Then people who do actually real hardcore solid state experiments, neutron scattering experiments of dynamical structure factors. They also, I mean, these experiments, of course, are done for many years, but they've been able to look into them from the different angle in 21. This is a group of Alan Tennant from Oak Ridge, and they found consistent data, which again is consistent with this 3/2 scaling. So, and then there are most recently there was an experiment on not only on the scaling but on the full counting statistics, that is on the distribution, not only on the dynamical growth, right? Not only the first or second moment, but on the full distribution of the, let's say, the number of quasi-particles that cross a line. I mean, the idea is basically you take a large system, infinite system, you divide it into half-infinite pieces, and then you count how many particles or quasi-particles or charge, actually, in this case, magnetization. You count total magnetization, which crosses an imaginary line, dividing the two halves in time t. And that you compute the full counting of this object, right? I mean, and this actually can be measured now in this modern quantum simulation devices, these quantum computers, as people want to call them, and and you see that you have. I mean, I just show one figure from this paper, but it's kind of interesting that okay, first we find the correct dynamical scaling exponent, but second, we find that the fluctuations are not those predicted by KPZ. So this is extremely, I think, important and interesting. We found a universality class of integrable models for which 2-point functions follow KPZ, but higher point functions are completely off. And they have to be off because the models are at equilibrium, so the distribution has to be symmetric. And KPZ is not about equilibrium. Height function is just growing, right? And so its distribution is asymmetric, it's skewed. So like typical distributions for different boundary conditions like Tracy-Witham or Bakes-Rains, they're all skewed. They all have finite skewness, but our data for these models are unskewed, and they have kurtosis, which is compatible with the Gaussian. So no kurtosis. Okay, so now this is just data, and now let's see what we can do with some mathematical physics, possibly. And for that, we have to identify simplest models for which maybe one can do something. And actually, it turns out that what I've just told you is not tied to quantum physics. It also happens in classical integrable models. So I will now discuss a family of classical integral models with arbitrary compact Lie group symmetries. So with arbitrary, if you want SUN, I mean, just to be simple, let's assume they have SUN symmetry. So arbitrary SUN symmetric chains, which are propagated in discrete time. So they are kind of automata, cellular automata, but with continuous variables, right? So each dynamical degree of freedom. I mean, I will just start with this figure, then go back. So this is a situation like this. You have, again, a space-time fabric, like a square lattice. Then you start with initial data, which is this line below, and then you propagate it towards upwards, right? And then you apply dynamics in terms of simple machines, simple boxes, which operate on 2 degrees of freedom at the same time. So they map these 2 guys there, these 2 guys there, these 2 guys there, and then you do the slight one-side translation so that you couple also these 2 guys to second and third and so on. So you do what we call a brickwork circuit, but of classical maps. Each of these maps is a symplectic map, so it corresponds to, if you want, to dequantization of some unitary dynamics. So now it's important everything is discrete. So, I mean, these models, even though they're classical, they smell a little bit like quantum systems because of discreteness, as you will see. I mean, there will be kind of quantum Young-Baxter equations appearing here in this model, not classical because of this discrete nature of time. Anyway, so but let's start from something very simple. And I try to advocate, I mean, that this model is really, to my view, the simplest model you can think of, which has non-abelian symmetry and which is integral. So I try to inspire this model, even though I give you the map right away. So this is a symplectic map. Dynamical degree of freedom is a matrix. I will state later more precisely what is the manifold, what is the phase-space manifold of the matrices that we consider. But now for the moment, let's just consider it's a Hermitian matrix. Or for the moment, even any matrix, right? You have a pair of matrices, M1, M2, and then you define a map which maps a matrix M2 to an image of matrix M1 by conjugation with the sum of matrices plus I tau. So tau is a formal parameter which will correspond to time scale, to the Trotter time, if you want. So this map, okay, this map is a composition of a swap. It swaps the 2 identity of the two particles, and then it makes a conjugation, simple conjugation with the sum, right? And this map has several cute properties. First of all, its inverse corresponds to the map for minus negative time. Second, it conserves not only hermiticity, it conserves also the square. So it conserves, if you limit yourself to a compact subspace of matrices which are Hermitian and square to identity, then these properties, both of these properties are conserved in time. And not only that, it conserves the sum of the 2 matrices, which means it conserves an SUN magnetization, if you want. So, I mean, let me be more precise. What is the phase space? No, the phase space is just what people call complex Grassmannian. So you should decide on the rank. So you take a dimension of the matrix. There are 2 parameters, dimensionality of the matrix N and the rank K. And so then these matrices corresponds to finite rank projectors of matrices of complex matrices of rank, Hermitian matrices of rank N of dimension N by N. So of course there is this matrix is square to 1, which means there are projectors. So they can be obtained from projectors by multiplying by 2 and adding or subtracting 1, right? So the spectrum of these matrices is composed of plus, minus, minus 1, but you can also replace minus 1s by zeros and then have projectors, right? So anyway, for convenience, we just take this type of matrices which square to 1, and you can of course parameterize them by SUN matrices, right? Which just conjugate these diagonal signatures. Anyway, this is the phase space, and so we have now the many-body map, right? Composed of these simple 2-body maps, on a many-body phase space, which is a Cartesian product of this kind of compact Grassmannians, complex Grassmannians. Okay, but how do we derive this map? How do we argue that this is an integrable system? Let me try to prove you that this is an integrable system by deriving it from a parallel transport problem. So let's just take a simple transport problem in Cn, so in a vector space of n dimension, complex vector space of n dimension n. And we ask the following things. We have two propagators. Now we have a square. This is all discrete, right? Space and time is discrete. So these guys propagate diagonally this towards northeast and towards northwest, right? So there are 2 guys, northeast and southeast, right? Let's decide that they are what we call L plus and L minus, right? So first, we don't want to break any symmetry, so we assume that these are minimal, I would call minimal set of assumptions. Let's assume that L plus is the same as L minus, so let's call it just L. which depends on dynamical variable, which sits at the link of the at the link, right? So this is now the lattice of transport, but now the dynamical degrees of freedom sits on the links between two vertices of the lattice. And so this guy L plus just transports variable from here to here, and it depends on the matrix variable on the link and on the spectral variable lambda. Yeah. So now you want that the composition of these two guys is the same as composition of these two guys, right? This is commutativity, or kind of discrete zero curvature condition. Now you could include also an additional twist F, but now let's forget. I mean, this will be kind of a SUN magnetic field, but let's forget about the twist for the moment. Let's put it to identity. So what you need now is just L plus L minus M2 M1 is equal to L minus L plus M2 prime and 1 prime. So that's the image, right? That's the image of the map. So the product of these two guys should be equal to these two guys, and this should fix uniquely the map M1 M2 to M1 prime and 2 prime, and it does, right? I mean, it's a kind of, I will not do the calculation, of course, here, but it's a 10-minute calculation to convince you that this is indeed the case. This uniquely fixes the map, and that's the map I just showed you. So that's the map. Okay. So now what I claim is that this model is completely integrable. Of course, it's kind of obvious already from the construction, but now let's construct the transfer matrix of this model. I mean, let's construct conserved quantities, right? Okay, so now what do? We construct, I mean, this model is defined, of course, on this kind of skewed diamond lattice. So we have to define a monodromy matrix, which also will have some sort of staggering built in, but nevertheless, it can be introduced in quite an elegant way. So let's just take these Lax operators, which I just introduced, right? Lax operators now are n by n matrices, right? Which depend on spectral variable. So now let's multiply this. Now let's define what I call a monodromy matrix, which is a product of Lax operators. And monodromy matrix depends on the whole string of initial data, right? Initial data now is a string of matrices, M1 to M6 here. So M1 to ML. So the system size is L. So a string of initial data, we multiply Lax operators, evaluate it at the initial data, and this gives us what I call a monodromy matrix. And then I will introduce this transfer map, now which is no longer a matrix, I call it a map. Why a map? Because it maps, dynamical variables, a string of initial data, which is the phase space point, to a complex number, right? So basically it's an observable. It's a nonlinear observable, right? It's a kind of phase space function. Yeah? So now we define this dynamical map simply by trace of the monodromy, and now what we claim is that this guy is invariant under dynamics, right? So composing this dynamical map from the right with dynamics, with this full kind of string of gates, right? Even and odd string of gates, you get the same map back, right? And that's actually something that directly follows from the zero curvature condition from the definition of the map. It's easy to imagine, I will not prove. And then you can also prove something more. You can prove that there is a Poisson bracket, which I also don't want to introduce because I have not so much time. But believe me, there is a nice, basically the correct kind of SUN Poisson bracket in this case, which with respect to which these two transfer maps commute, right? They are in involution, right? So that would be kind of the integrability structure of this model, right? And that actually gives us conserved quantities, right, through logarithmic derivatives at special points. Now, these special points can be sought for as points for which Lax matrix becomes of low rank, right? Now, if you look at least the reference where I learned this from was again textbook by Tafadiev and Takhtajan, and they tell you that if to get local conserved quantities, you have to find points of spectral parameter where Lax operator degenerates to rank 1 matrix, right? Now, in this case, this can only happen where you have rank 1 Grassmannian phase space. Where you have higher rank Grassmannian phase spaces, this will not happen in general. So you will not have local conserved quantities. So I think that's kind of interesting. You have an integrable system, but I don't think you can find local conserved quantities. At least it's not obvious to me. Okay, so now you can do the continuous limits, and then in continuous limits you can find, let's say, Hamiltonian continuous time limits. You can find more kind of familiar integrable Hamiltonians. For example, if you include the twist, I just said I would skip, but if you include a twist, you get magnetic field. And then you get this kind of Landau-Lifshitz-like or Ishimori-like SUN version of Ishimori Hamiltonian on the lattice. You can do additional continuum space limit. You get kind of SUN version of Landau-Lifshitz field theory. In any case, what is interesting maybe is an example for n equal to 2 or k equal to 1, which corresponds to classical spins, points on a sphere. Then Grassmannian is just a two sphere. And for that, we have a very simple map, which is written just in terms of dot product and cross products, in terms of two spins. So that's the map. And that map has been actually used extensively in the recent years for doing numerical simulations because it's extremely easy to simulate it or extremely efficient to simulate it and to just learn about correlation functions from numerical simulations. And this is what happens if you do that for these matrix maps. You find 2-point functions. This is for different cases, different values of n and k. So n going from 2 to 5, and for all possible ranks. You see that it doesn't really matter whether rank k is 1 or not higher than 1. All these kind of scaling functions are, I mean, here to the I looking the same. If you just look at how they decay at x equal to 0, at shift equal to 0, you will see that they decay with dynamical exponent, which is all the same 2 over 3, right? So it's basically just arguing that this kind of conjecture on KPZ scaling does not depend on the underlying Lie group symmetry. For any higher rank Lie group symmetries, as long as they are non-abelian, you have the same kind of scaling. Not only that the scaling exponent is the same, but also the scaling functions are the same. Now, when you include magnetic field, you can have some more interesting phenomena, which I will skip. And now you can break integrability. And then there was actually initial claims that some of these phenomena can actually survive integrability breaking, which we doubted. And because in the first paper on classical chain with Giga, my student, we actually argued against it. But then there was actually two papers recently, last year, that actually argued again consistently that after you break integrability in these integrable models with SUN symmetries, you actually have a very, very long transient times to diffusion. But eventually you get diffusion, but with times which go with higher inverse exponents of coupling constants, like even lambda to -6, depending on whether you have energy or non-energy conservation. So I will conclude now. So the take-home message is that we believe there is a very interesting conjecture on superuniversality of superdiffusion. Well, it's a bit of provocative combination of words, right? But still, I mean, when you have an integrable model, then all these integrable models in terms of time-dependent statistical physics, they will behave very similarly as long as they have non-abelian symmetries. This holds in quantum and classical magnets. Let's call these systems magnets. But you know, we'd really like to have some proofs of this observation. So I think this is an interesting problem which I want to kind of engage in future. And yeah, I hope that there will be some progress. Thank you.
Questions, please. So I just want to make a small short comment. I think that the scheme which was explained can be applied to all quasi-classical limiter for all spin chains for affine Lie algebras. So we need just carefully do quasi-classical calculation and replace the evolution using the conjugation with the R matrix. Classical Yang-Baxter equation.
Yes, I believe so, yes.
Thank you again for interesting talk.
Thank you.